All right, guys. So welcome back. We are here to go through the energy and momentum review. So the topics are listed, and the type of situations you're going to have to do with work, power, energy, conservation of energy, and momentum, impulse, collisions, conservation of momentum. So the first one here is it says a ball is traveling at 6 meters per second and has a speed of or has a mass of 0.5 kilograms. So if I just kind of draw this out, that's our initial kind of stuff, VI. And then it hits a wall and it bounces back off the wall at a final velocity of 4 meters per second in the opposite direction. So this would be like a -4 meters per second, and this was like a +6, if we want to just kind of make sure that we understand that. And we want to find the impulse acting on the ball. So change in momentum, or impulse, or delta P, is the final minus the initial. We could also try to use a different equation, which is that F delta T equation. But we don't have a force, and we don't have a time of impact, like how long the ball is in contact with the wall. So this change in momentum one is going to be the one that we want, and we know that P equals mv. So we really just have to plug into P equals mv twice and then subtract, and that's about it. So for the final, it would be 0.5, which is the mass. So that's what I'm putting in for mass here. And then the velocity final was -4. So 0.5 times -4. And then I'm going to subtract the initial, which was 0.5 times 6. And that was a +6 because it was going to the right. So half of -4 is -2. We're going to subtract off half of 6, which is 3. So the change in momentum of this ball in this collision is going to be a -5. And this would be kilograms meters per second, which is the unit for impulse or change in momentum. So that's essentially it for this problem. It's pretty straightforward. There could be a follow-up, like if they gave you a time or they gave you a force, they could ask for those other pieces, but I didn't do that in the review, so I'll keep it moving. Okay, so the next one is another situation where it's conservation of momentum, and there's a bullet which has a mass of 0.003 kilograms and is going at 1,000 meters per second. It's going to run into this block that's kind of just hanging here, which has a mass of 2 kilograms. And we're going to try to figure out, after the bullet gets embedded in the block, what is the speed of the bullet block system after the collision. And then we're going to calculate kinetic energy before and after, and that's going to help us decide the type of collision that it is. So we're going to go ahead and try to figure this one out. So just let me try to get the pen a little nicer. Okay, so again, with any collision situation, you're going to use conservation of momentum. So for part A here, conservation of momentum says that as long as the system doesn't have any outside forces or external forces acting on it, that the total momentum in the beginning should equal the total momentum at the end. And that poorly drawn sigma just means add all the momentums together. So if we look at before, which is like before the bullet gets embedded in the block, and then after as our final, the before, the only thing that has momentum is the bullet. So what we're going to do is we're going to do, again, P equals mv. So it's just this basic P equals mv equation for each one. So the bullet has a mass of 0.003, which is pretty small, and the block, or the bullet, is moving at 1,000 meters per second. Now, I didn't worry about calculating the momentum for this block because the block isn't moving, it's at rest. So since it's at rest, you don't have to do anything, it doesn't have any momentum. Afterwards, they're stuck together, so the bullet and the block are together, so I'm going to add them together. So it's going to be 2 plus this 0.003, so that'll be 2.003. Sorry, my handwriting using the mouse is not so good. And we're looking for this final velocity that it ends up with. So essentially we're going to do this math. 0.003 times 1,000 is just 3, and then it's 2 times, or 2.003 VF, and we're going to solve for VF. So you just divide through by that value, so the 2.003 on both sides. And I'm just going to write it once because my computer's being wacky. So that's going to cancel over there. You divide that out, and you get about 1.5. So VF is a little less than 1.5. It's like 1. It's supposed to be a 1. There we go. 1.498 is what I got. So like I said, really close to 1.5. And that's it. So that's part A. That's the final velocity afterwards. It makes sense, right? So like the bullet is going really fast in the beginning. It slows down quite a bit when it hits the block. The block is going to start moving. So again, it's like the bullet loses momentum, the block gains momentum, but the total momentum is conserved. Part B and C are very similar, where you're going to calculate the total kinetic energy. So add up all the kinetic energies. So sigma again, K for kinetic energy, or KE, it doesn't matter which, before. And before it's just the bullet. So it'd be 1/2 the bullet's mass, which is the 0.003. And then the velocity of the bullet by itself is 1,000. And because it's going so fast, it has a lot of kinetic energy. That's why bullets are dangerous. Make sure you square that 1,000. And when you do that, you'll get a number like 1,500 joules of energy. So 1,500 joules is the amount of energy that the system has in the beginning. For part C, it wants it afterwards. So afterwards, our situation has changed a little bit. We have both those things moving. So for the final kinetic energy, we do 1/2, and then the total mass, because they're stuck together. So the total mass of this thing is that 2.003. And then we're going to use our answer for the velocity, which was 1.498. And again, make sure you square that velocity. And only the velocity, not the whole term, just the velocity term. So when I did that, I only got 2.25 joules. So the energy, 2.25. So a lot of the energy that it started out with in that collision, a lot of the energy went into deforming the block, a lot of heat, a lot of sound in terms of kinetic. Also, this, if it was on ropes like it is in this picture, it would swing upward, so that kinetic energy is also going to transfer into potential energy. So anyway, that's the energy transfer. So we've done A, B, C, and D is asking for us the description. So they stick together. So the two objects are basically becoming one object. And the kinetic energy, the total kinetic energy initial is not equal to the total kinetic energy final. So with those two facts, this means that it is a perfectly inelastic collision, or a pi collision. So that is the type of collision it is. All right. For the third problem, this one is talking about a 2 kilogram object initially is at rest, experiences the forces described in this graph. So it's force versus time. So it's showing you how much force is acting on an object for the amount of time that it's acting. And based on that, we are supposed to try to find the change in momentum, which is the impulse again. We did problems like this in class when we were learning about it, but on a graph of force versus time, the equation for impulse or momentum with a graph, or with impulse so for impulse it's force times time. So that's essentially what we're going to do here. So when we do that, we're going to find the shapes and the areas. So basically we're going to need to find the area of each of these pieces and add them up to get to the total change in momentum. Okay, so if we do the first section here, this is a triangle. So for this area, it would be 1/2. It is 1 second wide, and it is 2 newtons tall. So if I multiply those out, 1/2 and 2 just cancel, and I get 1 for that section. This triangle is exactly the same amount as the triangle we just calculated. So again, it's 1/2 times 1 wide and 2 tall, so that would be a 1. And then finally, this shape here is 2 by 2. So this rectangle or square is 2 by 2, so that would be 4. So if I add all those together, I will get the total change in momentum, which would be 6. And we could call this Newton seconds because that's the units that we were working in. So newtons for force and seconds for time. Or we could do kilograms meters per second. It's the same thing. This is a positive area, so this is a positive change in momentum. So for part B, it wants to know what's the final velocity of this object. So we're going to use the other change in momentum equation for this one. So it's the change in momentum is the final minus the initial. And we're going to do the change in momentum was 6, positive 6. The final momentum, it deals with the mass, which is 2, and the final velocity, which is what we're looking for. So VF, the speed at the end, is what we're looking for. The initial momentum would be 0 because it's at rest, so it would be 2 times 0, so that's just 0. So we just have that term going away, and then we divide through by 2, and it's pretty basic. So 6 divided by 2, not too mathematically challenging. VF turns out to be a positive number, and that makes sense because it has to be positive in order to, if it's not moving and it has a positive change in momentum, that's going to be a positive value. So it ends up going to the right at 3 meters per second. The force is also directed to the right, so the force is positive. So if you imagine you had some object, this box, and we started pushing on it to the right with a positive force for some period of time, it's going to gain a positive momentum. And because it has a positive momentum, it has a positive velocity. So those ideas are always in agreement in terms of this object was at rest in the beginning, so VI was 0. The only way it wouldn't be that is if it was if it had some big initial velocity going to the left and then the force was not big enough to make it stop and turn around, which is possible as well. All right, so a couple more of these problems here. There was a small typo here. It should be object. So it says an object is lifted vertically 2 meters and held there. If the object weighs 90 newtons, how much work was done lifting it? And then the follow-up to that is if it takes 3 seconds to lift this object, how much power was used? So we could think about work. We're going to think about power. So for the second part, we're going to use the power equation, which is work over time. For the work equations, we have a couple options. So we could talk about FD cosine theta, which some people like, and if you want to use that, you could absolutely use that in this problem and figure it out. Or work is also equal to the change in energy. So if I draw this problem out, there's some object, so I'll just make it a box. And we're going to take it from the ground and lift it up. So it's going to lift up to this new position up here. So the distance or displacement is going to be 2 going vertically. In order to lift it up, you're going to have to push up. So this is similar to what you did with the bleachers. And this 90 newtons is the weight. So that's the force of gravity. So the force of gravity on this box is 90 newtons. Trying to let this catch up. There we go. 90 newtons. And in order to lift it, this force applied, or your pushing force, has to be equal to that. Otherwise, it would not move. So again, kind of thinking through those. So if you think about the forces going up of 90 and you're moving at 2, and that angle between them is going to be 0. So if you want to do this, it would be 90 for the force and 2 times the distance. And cosine of 0 is just 1. So you would just go to 1 there. So this answer for the first part is 180 joules. Say you didn't like that equation, that confuses you. If you use change in energy, it also works. So for change of energy, in the beginning, if we look at this, I would say it has no energy because it's not moving. It doesn't have any kinetic energy. There's no spring, so no elastic, and it's resting on the ground. So the object doesn't have any gravitational. When it gets up here, though, it definitely does have the UG, or gravitational potential energy, and the formula for that is mgh. So you could look at it this way. This would be the final energy that it had. In the beginning, it didn't have any. So if we're going to do work equals change in energy, which we can, I would say it's at the end, the final, it's got UGF. And at the initial point, it didn't have any energy. So it's just whatever this final potential energy is how much work was added to it. So again, you're taking some object, if you're doing the bar graphs with the LOL graph, there was no energy over here in the beginning. we added some work, and then we ended up with the UG. So again, it should make sense conceptually there that this work is equal to whatever that amount is there. So for MGH, that's a pretty basic idea. So the height would be 2. mg is really the force of gravity. Like if you remember the equation for the force of gravity, it's m times g, so that's just 90. So it'd be 90 times 2 again, and it gained that energy, so it'd be positive. So this is just a positive 180 as well. So so any of those ways of solving that first part is fine. For the second part, you're just going to take the energy or the work that was changed, and that would be 180. And you're going to divide it by the time that it takes for that to happen. So it was 3 seconds. So if you divide 180 by 3, you just get 60, which is a fairly easy number to calculate. So that's why I picked that. I don't know why it's being so laggy. Okay. Sorry about the delay here. So it would be 60. So 180 divided by 3. Really slowed down here. My computer's, I think, dying. So 60, and it's power, so it's watts, like light bulbs. You could write capital W, that's the same thing, but watts is the official unit. Okay, a couple more. Hopefully my computer holds out. So for the next one here, it says a toy roller coaster is moving at the top of its first hill, as shown here, and it tells you the height and everything of the roller coaster. It's a toy roller coaster, so it's not really big. It says calculate the speed of the coaster when it reaches point A. So we're comparing the energy at point A, which is here, to the energy that it has here. I would say there aren't any outside forces. So if we're doing this idea, we could say at this point, again, the LOL chart is a good way to kind of organize your thinking. And I'm not worried about the values or anything right now, but we got motion, so it's got kinetic energy in the beginning, so it's got some kinetic energy. I would say it has height. So it's got gravitational potential energy, so I'll have those there. In our system, it's just the coaster car and the Earth. Okay. If we wanted to include the track, we could. That's okay. We're going to assume that there's no friction right now. I think in a later part of the question, it asked about that. So that's our initial energy. At the end, at point A, if we're measuring the energy there, what's happened to our height? So if we look at our height, that's gone down a little bit. So the gravitational potential energy should have gotten smaller. So I'm going to make this bar here bigger, and this point A is a little bit smaller. So I'll still make it a little bit bigger than that, but this is smaller than that. And then because of that, if there's no other energy transferred in or out, the kinetic energy got bigger. But if you add these two together, the kinetic energy and potential energy initial, and you compare it to the kinetic energy and potential energy at point A, they should equal the same total amount. So whatever this total bar was, if you remember the skate park, if you add those together, these should be equal. So this total energy initial should be equal to the total energy at A. So again, that's just the conceptual way you approach this problem, and it's really just plugging into the different values for those different equations. So I don't think there's any work going in or out, so that would be 0 there. So it's just the total energy initial is equal to the total energy final, or the final point that we're measuring is point A for right now for part A. And we would say this is kinetic plus gravitational at the initial points should equal the kinetic at A plus the gravitational at A. And sometimes this is confusing for people because they're like, well, I'm just looking for a speed. So can I just do kinetic energy? Yeah, I mean, that's where the speed is going to come in here. We're going to look for VA essentially. But you got to understand the other energies and how they're transforming and transferring in order to be able to solve for that. So we're just going to plug in the values now. So kinetic energy is still 1/2 mv squared. We've done that in other problems, so don't really need to write that out again. But 1/2, the mass is 0.5, and it's going at 1.5. So we're going to do that in the calculator and get that value. And then that V is squared. And then for MGH, we're going to use the formula for that. So it would be 0.5 for the mass. It's a 0.5. Gravity is 9.8. And our height at the very beginning at the top of that hill is 2. So that is the left side of the equation. On the right side of the equation, we can plug in the same ideas. So this is 1/2. We're just looking at the ideas at point A. 0.5 is still the mass of the car or roller coaster. We don't know the velocity today. That's what we're solving for, so that's our variable. So VA squared there. And then we can do MGH. So M is 0.5. G is 9.8. And the height is, if you read this carefully, it's 1.9. So the radius of the circle there is 0.95. So if you add 0.95 and 0.95, you get the total height, which would be 1.9. So you're going to go ahead and plug those values in. I'm not going to show that on the calculator here, but if you plug them in and then add them together, you should get 1 point. Oh, sorry, I can be a little more specific. I found where I showed the work on my paper. So if I do 1/2 times 0.5 times 1.5 squared, you get 0.5625. And then you're going to add half of 2 is 1, and 1 times 9.8 is just 9.8. And then that's equal to 1/2 times 0.5 is 0.25 VA squared. And then we're going to add 0.5 times 9.8 times 1.9, and that's 9.31. We're going to take all the non-VA terms to that side, so we would subtract and then get a number. That value is like 1.0525. And that's equal to 0.25 VA squared. So just, again, working through the algebra with you guys. And then you divide by 0.25 on both sides. So it cancels out over here. That's VA squared. We don't want squared, so we got to take a square root. So we got to take a square root of that value. And finally, for the answer for VA, you should get, at position A, the velocity I got was like 2.052. That's supposed to be a 2. There we go. That looks better. And that's meters per second. So that is the answer to part A, 2.052 meters per second. It is sped up a little bit. So like it was going 1.5 before, 2.05 is faster. That makes sense because it went down a hill and it's at a lower position, so it should be still moving. It's not tremendously faster, but it is something. Okay. For part B, it says if at the end of the track, so if we imagine the track comes all the way down somewhere like here, and the height is 0 now, we want to know what is the speed at that point. So really the total energy in the beginning is still the same. So we're just comparing the total energy initial. But now this final energy, or the energy at point B, if we call that position B, if we think about it, the thing that's changed is there is no more, if we had a different bar graph for B, it's still got kinetic energy. The gravitational potential energy is no longer there. So that one's 0. So the kinetic energy is going to get bigger, which is going to be equal to the total again. The total is still going to stay the same. So we can kind of work from that. So if I add these two numbers together, I get 10.3. That's supposed to be a 3. So the total energy in the beginning is 10.3625. That's the total energy that I started with here at this position. And then now it's all transferring into kinetic energy. So for kinetic energy, it'd be 1/2. The mass is still the same mass. That's supposed to be a 2. So the mass is still 0.5. But this time, this would be the velocity at B. So it's going to gain more speed in this situation because it's dropped the whole 2-meter height, and that's going to increase it quite a bit. So again, half of 0.5 is like 0.25, so you're going to divide through by 0.25. My 2's are not showing up very well. That's better. So that'll drop out over on the side. It's being really slow and laggy. And then again, just like we did the last time, we got to take a square root to solve. So we'll take a square root of that value. And the velocity at B turns out to be 6.44 meters per second. So as I said, and it makes sense, that it should have kind of gained a lot of speed. 6.44. I'm not sure why it's being so difficult. It should have gained a lot of speed because it has dropped a good amount of height, 2 meters. If you drop from 2 meters, that's going to make you speed up quite a bit, and it was already moving. All right, so the last part here is part C, and part C wants you to calculate if the lowest point of the coaster, it only had a speed of 2, so it's not going this 6.44 like it should. It's only going at 2. We want to know like how much friction converted energy into heat and sound. So again, it's sort of a different situation. We're not going to have all kinetic energy this time. We'll have some kinetic. If it's going 2, it's got actually almost the same that it did at point A here. So it's got some kinetic. The total energy is still the same, and we need to figure out how much this non-mechanical part is. So that's the enemy. And that's why I included the track as part of our system. So this non-mechanical energy. So for part C, it's really similar in terms of setting up kind of conservation of energy. We're just like looking at a slightly different situation. So there we go. So the total energy at A, which is the initial total energy. Total energy initial should equal super lagging total energy at C. I just have to speak slower to make the writing catch up. So again, it's that 10.3 625. That is the energy that it has in the very initial point where it's at the 1.5 meters and moving. I'm sorry, it's 2 meters and moving at 1.5 meters per second. And then this is going to be, it's going 2 meters per second, so 1/2. The mass is still 0.5. This time it's going at 2. The velocity. Make sure you squared the velocity. And then whatever the difference is just this non-mechanical energy. So if you do this calculation here, this amount is just 1. So half. 2 squared is 4. 4 times a half is 2. Times another half is 1. So you're basically going to subtract 1 from both sides here. And get your answer. So the answer for the non-mechanical energy, the amount that the non-mechanical energy is 9.3. So 9.3625 joules. And this is, my computer is, I think, really about to die, so I apologize for this difficulty with me writing on the screen and recording at the same time. It's just not working very well. So we got one more to do, and that's number 6. So let me get to that one here. All right. So number 6 is another energy-based one. So it says a 2 kilogram mass is attached to a spring with a force constant of 19.7 newtons per meter. Initially, the mass is compressed 20 centimeters from position B to position A, and then it's released and it oscillates back and forth. So like at rest, it's just here, and then we applied some force to make it get to position A here. So the block gets there. Obviously, the spring's going to get compressed when that happens. And then we let go of it, and it starts oscillating back and forth. So when it oscillates, it goes back and forth from position A all the way to position C and then back, and it goes through point B. This situation we're going to look at in the last unit of study, so we'll come back to this again, but you can get a preview of it now. So it says, for part A, how much work was done on the mass spring system to move the block from position B to position A? So again, we're looking for work. And we don't know how much they actually pushed. So I think we're going to have to use the change in energy situation here. So change in energy. So in the beginning, before anything was pushed or pulled, there wasn't any energy there. So it's just when we compress it to A, what kind of energy does it have? And I think it has a spring potential energy. So the spring potential energy at A is what that's supposed to be an S. At A, that's the type of energy it has at that point, and before that it didn't have any, so that's going to be minus 0. So the work that is done on the spring block system or spring mass system would be the spring potential energy, so that's 1/2 K, which is 19.7. That's the spring constant. And then we need to figure out how far it was compressed or stretched. So let me write out that equation because I kind of jumped over that. So it's 1/2 K X squared. So K is the spring constant, and then X is how far you've compressed or stretched it. So if this whole distance here is 40 and it says that it's compressed 20, so it's 20 centimeters, which is 0.2. So you got to convert from centimeters to meters. That's the only bit that's a little bit tricky. And if you do that in your calculator, you do this calculation, you should get something like 0.394. So that is how much work was done. That is how much energy was gained by the mass spring system. Okay, so for part B, it says at several points during the oscillation, the mass is 10 centimeters to the right of position B. So it's like over here somewhere. And we want to know what's the speed of it when it's moving at that point. So we're looking for how fast is it moving at position, wherever that is. So so again, it's just conservation of energy. So the total energy initial should equal the total energy at any other point. I'm just going to write, I don't know, whatever that is, the star asterisk, whatever we want to call that. So the total energy at that point. So we already know the total amount of energy or the work that it starts with was just 0.394. When it's at this position where I put this asterisk, the 10 centimeter mark, it's got spring potential energy. So it's got spring potential energy there. And it also has kinetic energy because it's moving. So we'll learn later on that it's actually moving fastest when it's not compressed because all the spring potential energy is changed to kinetic. So it's got some of each here. So the kinetic energy at the star or whatever, we labeled that. So we're going to do the same equation for spring potential energy. It's just a different compression or stretch. So when it was maximum, it was all compressed. It was 0.394. This time we're going to do 1/2 the same spring constant because the spring didn't change. It's still 19.7. And then now, instead of having 0.2, we're going to have 0.1. So 0.1 squared, that's going to be the distance stretched or compressed squared. And then we're looking for a velocity, so we got to use kinetic energy's equation. So that's 1/2. The mass of the block is 2, and then we got v squared. And we're looking for this velocity at this point. So that's it. So we're going to do that equation and do the math here. So when I did this, I got 0.394 still on the left. And then 1/2 times 19.7 times 0.1 squared got me 0.0985. Again, I might have rounded slightly, but it's okay. If you do or don't, it's not that big a deal. And then 1/2 of 2 is just 1, so this is just plus v squared. So we're going to do the normal kind of subtract and isolate the missing term. So I'm going to subtract 0.0985 on both sides, and then take a square root. So the value, it turns out to be, when you subtract, is 0.2955 is equal to v squared. and then you have to take a square root. So we'll take a square root and take a square root. And this velocity at this point is 0.544 meters per second. So it's definitely moving there, and it's 0.544 meters per second is our answer for that position when it gets to 10 centimeters. The last part here, so that was part B. The last part here asks us to find how far is the spring stretched or compressed when it's moving at 0.4 meters per second squared. So if we think about this, 0.4 is less than, or 0.45 is less than 0.544. So I would say it's closer to the extreme points. So like the extreme points is where it stops and turns around. So this would be like 0 velocity at A and 0 velocity at C. So it's somewhere kind of over here past the 10 centimeter mark this way, or over here somewhere past the 10 centimeter mark over there. So we're going to be able to figure out that in a really similar way. We're going to use conservation of energy. It's basically the same setup for part C here. Let me change color so it looks a little different. Okay, try to make it a little thinner as well. Okay, so again, total energy initial, the very total energy, the work that we put in, that's the energy that's in the system. Again, we're assuming no friction, doesn't talk about any friction. That's going to equal the energy that it has at this new position here, which is what we're trying to find in part C. So this 0.394 is the energy that it starts with. And then we have to consider the energies that it has at this point. So at this point, it's got kinetic and potential again. So US plus the K plus the kinetic energy. And instead of looking for velocity this time, we're looking for kind of the X term. So we're looking for how far it's compressed or stretched. It doesn't matter if it's compressed or stretched. It doesn't matter if it's a positive or negative change in length of the spring. It's the same amount of energy either way. So it's 1/2. Again, our spring constant K is 19.7 in this problem. So that number doesn't change because our spring is not changing. And then X is what we're looking for. So I'm going to have X squared here. That's our formula for our spring constant, which we used up there. And then for our speed, we actually know our speed this time. So our kinetic energy would be 1/2. The mass is 2. Sorry, this is really frustrating a little bit to me, and I'm sure it's frustrating you too, but only a couple more minutes of it. It's not too bad. There we go. So 2, and then because the mass is 2, and then this velocity here is 0.45, and we got to make sure we square that term there. Okay, so again, 1/2 and 2 are going to drop out, so it's really just 0.45 squared. We're going to subtract that from this 0.394, and then do the rest of the algebra. So you get like 0.1915 as the energy. That is equal to 1/2 times 19.7 is 9.85. And then it's X squared. So again, you divide through by 9.85 on both sides, and then you take a square root, and you get X, and I'm just getting to the answer here because I'm tired of fighting the writing. X equals, maybe I'll get there. X is equal to 0.1339 meters. Okay, so that is your final answer for point C, or part C. So that checks out. So this was 0.1 when it was moving at 0.54. This is 0.14, so it's a little past that, and it's going to be slowing down as that happens. So the fastest it moves is at point B. I didn't ask you to calculate that, but you could. It would just be all the spring potential energy converts into kinetic energy at point B. And then every other place that we had, except for point C, if we got all the way stretched out, it has both these energies. So it has kinetic and potential anywhere else along the way. All right, I'm going to stop there. Have a good one. Talk to you later.